Okay, guys, I think we're on number 6 now of these short videos to go over volumes and plasma protein binding. So now we talked about rate of distribution, extent of distribution. We've talked about the different types of volumes, central volume, apparent volume, and volume of distribution at steady state. We talked about what determined that, which is what we're going to be working with most, is that volume of distribution at steady state equation. And we know that what is the most important component of that is the binding to plasma proteins and binding to tissue proteins. So now we're going to dig one more layer deeper and say, well, what determines plasma and tissue protein binding? Now, if you recall, we did talk about this last semester in 361. We talked about plasma protein binding, and we did the scattered plots and everything. You may not remember it, but it might be worth going back and looking at that. But I'm going to be reviewing what determines protein binding in this particular slide show, this particular component, this particular piece of, what do we want to call these little snippets? Okay. So why is plasma protein binding so important? And it really is. You'll realize as we go on how important this is. First of all, things are very confusing because usually when we're talking about drug concentrations, we're talking about total drug, which means both the bound and the unbound drug. So whether it's bound to the big honking protein or whether it's free, moving around, we add both of those components together to get the total concentration. However, if a drug is bound to a protein, it cannot interact at the site of action with the proteins or whatever it's interacting with to have its action. So only the free drug is actually pharmacologically active. So why don't we measure just free drug instead of looking at total? Because total is going to be confusing, isn't it? Well, it's a lot cheaper to measure total drug concentration. It's quite simple, cheap, and fast to measure total concentration. It's much more expensive and difficult to measure only free concentration. So when we get information back from the lab, it's going to be total concentration, both free and bound. Therapeutic range is almost always in total because that's what we actually measure. However, total can be misleading because if there's changes in protein binding, if more or less of the drug is free, then you're going to have more or less of the actual active component available to cause the pharmacologic activity. Now, the good news is that total will always reflect free as long as there's no change in binding. As long as the percentage of binding remains the same, so as long as only 10% of the drug is free, if the total concentration goes up, the free concentration will go up. If the total concentration goes down, the free concentration will go down. So as long as there's no binding change, as long as that percent binding stays consistent, then we don't have to worry. But if binding is changing, then total will not reflect what's happening with free. It might be misleading. We might see toxicity if more drug is free, even though the concentration hasn't changed. Total concentration hasn't changed, but the free concentration has increased because our fraction unbound has increased. So that's important to know. So as long as there's been no change in plasma protein binding, total will reflect what's happening with free, the active component. The other thing is plasma protein binding is really insignificant unless the drug is highly bound to plasma proteins. The more highly bound, the more significant changes become. We've talked about this a little bit in other contexts. So if the drug is 99% bound, that means only 1% is free, Then if there's even small changes in the fraction unbound, if it went from 1% free to 2% free, you've in effect doubled the active component of drug. So if a drug is very highly protein bound to begin with, we're going to be on high alert for changes in protein binding. If the drug is not highly bound to begin with, so let's say 50% of it's bound, 50% of it's unbound. If it changes by 1% there, then now it's 51% of it is unbound and 49% of it is bound. So it went from 50% unbound, to 51% unbound. Really, who cares? Not a big deal. So there's really little significance in protein binding changes unless it's highly protein bound. Now, students always want me to give them a number. I hate to give a number because it's just relative. The higher the binding, the higher the significance as far as changes in protein binding. But I did give you a number here. I guess I would pay attention if the fraction unbound is less than 40%. So as you get 60% bound or more, you should start to pay attention to protein binding. So what determines protein binding? All right, so here's free drug, symbolized by D. This is a concentration symbol, so the concentration of free drug plus the concentration of protein that's available to bind that drug, which is symbolized by P. Here's free drug, protein, and here's bound drug to that protein. So it can get bound and then it can become unbound. So this is a reversible reaction and follows the law of mass action. So this is the rate to binding, this is the rate to becoming unbound. So the concentration of unbound drug, which would be the active concentration of drug, would be this C with the U would be unbound drug. C with no label is going to be considered total. So concentration total times the fraction unbound will give you the unbound concentration. Does everybody buy that? I hope so. Concentration of bound drug. So concentration of bound drug is going to be equal to the total concentration times 1 minus the fraction unbound. So we all agree 1 minus the fraction unbound would be the fraction bound. So we would say fraction bound times total concentration to get us our bound concentration. So this would be the inactive component of the concentration of drug. Total concentration will be bound concentration plus unbound concentration. It also would be, this is of course bound concentration plus unbound concentration. And P represents unoccupied protein that's available to bind the drug. So if we go back to our simple interaction, free drug plus free protein will make bound drug to that protein. It can go both ways. Then if we look at our how rapidly this is happening, we have a Ka, or an association constant, which is going to be bound concentration over the product of the two entities. You don't have to worry about this too much, but it's all about that relationship between K1 and K2. The higher the Ka, the higher the association or the affinity of that drug for the protein. Kd would be the concentration of unbound drug when half of the binding sites are available. This should sound familiar. Concentration of drug when half of the sites are available or half of the sites are full. Depends on if it's you look at a glass of being half full or half empty. So Kd is actually a dissociation constant, but Kd also sounds like the Michaelis-Menten constant, doesn't it? And it is actually, in this case, the concentration where half Vmax. Here's the concentration where half of the binding sites are full. So you guessed it, this undergoes a Michaelis-Menten type relationship. Having my hot green tea, tastes delicious. Keeps my voice going here. Okay, so that's really about the affinity, isn't it? This is about our affinity between the free drug and bound drug, or free drug and free protein to make a bound drug. The capacity is going to be the total numbers of protein binding sites. So it's symbolized as N total. N is the number of protein binding sites available. So, all right, I'm not going to go into this too much, but fraction bound will be the concentration bound over total. Fraction unbound will be unbound concentration over total. Good. So here is our relationship between our bound concentration will be equal to our total number of protein binding sites available times our free concentration over KD plus our free concentration. So this should look very familiar. This is Michaelis-Menten once again, isn't it? So N total is our capacity of our system, or would be analogous to Vmax. KD is our affinity constant, the concentration where half of the binding sites are full. So, and of course our concentration component here. And this will tell us what concentration of the drug is bound. So what determines protein binding? Number of protein binding sites available. The KD, or the concentration where half of those binding sites are occupied, and finally the concentration of unbound drug available. Now, as you can see, well, I'm not going to go into this too much, but in this denominator we can see that concentration is a determinant of our concentration bound. So this allows for a nonlinearity, but I'm not going to get into that now. It's a little too confusing, so don't worry about that for now. But anytime you have a concentration here, we have the possibility for nonlinearity. All right, that's it for this one. Okay, we'll see you at the next one. Bye-bye.